Okay, so today what we're going to start with is you're going to turn in your annotated papers and you're going to get a stamp and then you're going to take them right back. Okay, this is me demonstrating, or this is you demonstrating that you did something. Okay, anyone have their paper?
Yes.
Okay, if you want credit for the first problem / thing, you will turn in your paper now. And your name is hopefully on it.
Yeah.
Yeah. Now note that I am not reading through your annotations to say, oh, you didn't annotate the things that I expected you to. I'm looking for progress. And I'm hoping that the progress that you're making in your personal work is reflective of your understanding, right? Yeah, see, I love this. This is good annotation. A little bit of words, a little bit of highlighter, underlining words.
Yeah.
You've read this paper already though, huh?
Yeah.
Damn it.
Great.
Yeah, you want to do the whole thing. Okay, but we're gonna still give you this because you started. Anyone else? No, that's good. This is how you're supposed to start. This is great.
Okay. Progress. Next time I'll do this.
Why is this? What's wrong with this?
Oh, no, I thought that was-
No, this is annotation. This is annotation. We'll talk about the specific way that we're focusing on it later, but that's annotation. Okay. That's okay. That's okay. Someone thought that we only had to do the abstract, so we'll talk about the whole thing. The reason that we're doing this is because in order to learn how to read and write scientifically, you have to practice reading and writing scientifically. Okay. So the more that you read papers, the more that they'll make sense. You'll understand the structure. You'll understand what it is about the scientific paper that should be warning you about different parts. At the end of today, you will get a new paper. You'll notice a little theme here. Okay. You'll read more. These, unfortunately, are planetary science paper. Oh, I know. It's okay. You'll survive. So while these will be on Mars, they actually lead a very interesting set of examples about how we assess credibility. So you'll see that the next week's class will be determining sources of credibility. That's generally applicable. That doesn't just have to do with planetary science, right? How do we tell whether or not a result that just came out can be accepted at face value? Okay, so we'll hand those out at the end of class. I had a great question already, someone who was looking too far ahead about some of the structure of the class overall. So you'll notice that there's this whole writing part here, literature review, hypothesis, review panel. Up here, you have this thing, review a grant. So this is where you're going to be learning how to write a proposal. And what I mean by that is it's not like in computational where you write a paragraph, hey, I want to study, I don't know, whatever it is that we did in computational. This is how you would scientifically write a proposal. How do we pitch an idea based on some set of, whatever paper or topic you're interested in? You identified a specific topic that you think you could work on. Now, in practice, you won't be able to do cutting edge research, right? Unless you have like a particle collider in your backyard. There's a lot of stuff that you might be interested in that we just don't have the resources for. So the project that you do and the proposal that you write are not necessarily the same, but they're practice. Does that make sense? If you want to, you're more than welcome to use it in your daily life. If you're planning to go to grad school, a great thing that you can do is in your last year of undergrad, you can apply for something called the FINEST, FINNEST, and it's a NASA proposal that would fund you in grad school. So you can bring them this and you say, hey, I have my own money. Let me in your grad school, right? So we can talk about that if you want to apply to that as well. Okay, to review a grant, you'll be doing literature review and hypothesis formulation. Notice the time between here. It's like a month. This does not mean that you turn in one thing and you never think about it ever again. In fact, I just handed you back that annotated paper. And what you're going to do is you're going to hand it to a partner later on in this class who's going to review your annotations, and you're going to have a conversation about, I didn't get this. Why did you highlight this and not this other thing, right? We'll talk about that at the end of class. Same thing will happen in Journal Club. Journal Club will be where you analyze these, you'll write summaries of them, and then you'll hand them to your friends. Okay. This structure starting to seem clear? Okay. Somewhere along the way, we'll start doing observations. So in order to start doing observations, we'll have to talk about the night sky. If you already know about the night sky, great. Try to stay awake. If you don't know anything about the night sky, great. Try to stay awake. Okay. And the idea will be that even if you really want to do a physics project, you might think to yourself, well, maybe I'll just come along and I'll look at the data that they're taking, right? And a lot of the different proposals that we could do for actual observations for a research project, they start now. So you could start doing observations today. You could take them over the course of the entire semester, and then you can analyze them. Okay. Questions before we get started? I mean, I guess we're already started, but before we go to the slides. All right. Yeah. I love my those are different papers. Okay. Let's keep everything. Whether that is a folder, whether that's I mean, however you want to do that. You can turn it in earlier too, right? So if you're done on Thursday, like, hey, I'm going to miss Tuesday's class, just make sure it gets into me before Tuesday. Okay. So we're going to talk about how we navigate in the night sky. We'll talk about journal annotation that we'll do today, and then we'll talk about what Journal Club means. Okay, how do we measure sky distances? So most human beings are roughly the same shape proportionally. Okay. So what that means is that if you stick your hand out, fully outstretched, and then you pull your pinky, can anyone do this? All right, everyone can do this? Good. So that is about a degree on the sky. So what that means is if you start here, and you start at John, and you move all the way around, and you come back to John, you'll have 360 pinkies. About. Right? These are rules of thumb or rules of pinky. So, we'll take them with a grain of salt. This one here, 3 fingers, that's about 5 degrees. You're saying, well, this is not 5 times larger than this. Yeah. It's about. You can't use your pinky.
You have to use his.
You have to use his pinky. Does that make sense why that wouldn't be the case? Okay, so you do this. Ready? You go 1, 2, 3, 4, 5. Roughly. Okay. Fist, about 10 degrees. Okay. Quiet in the classroom, right? 15. Cowabunga, 25. That's about how wide things are on the sky. So why do I tell you this at all? Because if you're looking at 2 different objects and you're wondering whether or not you could get them on the sky, you say, well, one's over there and one's 35 degrees. Well, that's over there. So it's going to be larger. So you'd be like, oh, okay, 35 degrees. Well, that's this one plus this one. All right. That's pretty far in the sky. Cowabunga? That is just a Santa Cruz thing? I don't know. I thought everyone knew Cowabunga.
Yeah.
Everyone knows Cowabunga, right?
Yeah. Michelangelo.
Yeah.
Surf's up. Oh gosh, kids these days. All right.
That or yeah.
Do your cowboy
Cowabunga?
Show me.
Like that?
Show me.
Like this? What? Oh God. I feel so bad about my own Cowabunga. All right. So these are good to within a factor 2. Okay. So that means that you're just getting, if you're telling someone 20, right? Just do that. That's about this. Right. And you'll notice, right, this and this pretty close. Okay. How does it work? Yeah, just like that, right? right? So if you're trying to tell someone where something is on the sky, right, you're like that. So if you notice, go out and look at the moon tonight. Is the moon up? Is it? Has anyone looked recently?
No, it was a supermoon a couple days ago.
Okay, so we never look at the sky, right? Because God forbid.
Because God.
Okay, let's have a look. So here is this wonderful little schedule. Okay, today is the 5th. The moon is
56%.
56%
Visible. For us,
visible. What is visible?
from our perspective.
Full. 56% full. You can always see the moon. You know that, right? Yeah, that's why, like, even when there's a crescent, you can see there's a dark side.
Kind of like that.
That's called the unilluminated side. Okay, but what really happens is that light bounces off of the Earth, bounces off of the dark side of the moon, and then back to us in something called Earth shine. So there's moonshine, and there's Earth shine. Yeah. Okay, I know what that means to y'all. Well, maybe not to y'all, but you know what that works, right? Okay, so notice what's happening here. I went through and I meticulously changed each one of these per the calculation of the fullness. So we had a full moon last Tuesday, almost. Now it's a little over half. In the week from next, it'll be almost new. And I don't need you to memorize these. You can use these as a reference.
Why was the moon so big like 2 weeks ago?
The moon was closer to us.
That's why.
Yeah. Yeah, astronomers, they hate this term blue moon, absolute garbage horseshit. The things that matter are new and full, and then close or far. That's all that's happening. So the moon is not on a perfect, I can never do this with this. Right? Okay, here's the Earth. This is you. What? Yeah, I'm not gonna draw it to scale. Okay. Okay, this is called perigee. This is called apogee. And you're thinking to yourself, what the heck do those words mean? What does apo mean? Far or away. Peri means close. What's a periscope? Yeah, it's a scope that makes things look closer. So when you're in your what are those called? The tubes? Submarine, when you're a submarine, you're like looking, you're like, who do we bomb? Oh, those guys over there look close, right? Peri, make things look close. And then G here just means the Earth. Or part of the orbit. Okay. So in a blue moon, right? Or a super blue moon or a super moon or some stuff like that. This is just when the moon is physically closer to us. So it looks larger in the sky. As I get closer to Kobe, you'll notice that my face gets larger in proportion. As you bring your fist closer to your face, it gets larger. Right? It's not moving in like physical size, but it looks bigger in the sky. Right? Okay, so you'll notice two other things here. You'll notice that on the right-hand side, the sunsets are changing. Right? These are the correct sunsets for these days. So now you'll notice there's a little bit of a hiccup right here. What happened? Time change, daylight savings time. Okay. So if you started to make observations, right, it gets easier through the semester. Because this is inside of class time. Right? This is when we start getting real sad. That's planned for November 7th, Sadness Day. Right? Because that's when class you'll be in class and it'll be dark outside when you get out. Oh no. Right? So that's the end of summer, but at least it won't be like boiling hot anymore. So if you want to start taking observations, say of specific objects that we're going to talk about at the end of this, right? You could do it all throughout the semester. Right? Questions? Okay. Let's do some just typical sky motion stuff. This is going to feel really disjointed, but you need to know all of this disjointed stuff, and then you can go out into the world. right? Remember that this is not a lecture. We sit down, we do X, Y, Z, right? This is an observational astro class. The writing intensive component we will do as writing, and the self-motivated project will be self-motivated. Look at the number of units you're getting for this class. And remember this, we're going to meet for 1 hour, but if you do nothing else outside of that 1 hour, you will get the equivalent of 1 hour out of that total in your grade. Does that make sense? So let's say there's 7 hours that you're supposed to do every week. You do one of them. What's 1/7 of your total A? Nope. That's bad math. Okay. Let's talk about celestial motions. That is the universe from our perspective. We tend to think of, if you're using a planetarium software, you tend to think of all of the stars as existing on this exterior sphere called the celestial sphere. So this is us, okay? That spins, right? The reality is that we are spinning, but we perceive this to be spinning, right? We look up, we see the stars move. We don't see our motion, okay? So another way of thinking about that is that they're all, instead of being at many, many distances, let's imagine that they're all at the same distance, and that thing is going to move around us. So we have a star here. What's that one? The North Star, right? That's one that doesn't move. Makes really, really small motions about this. And everything else seems to go around the pole. We watch, they go around, they go around, right? Okay. There's this thing called the ecliptic. Anyone know what that is? Ecliptic.
Related to
Not read.
the eclipse.
Nope.
Okay. Is that like axes playing? Yeah. That's what we're thinking about.
The plane that what's rotating about?
The Earth.
So this is the plane in which the Earth lives. Okay. So as it goes around the sun, you'll notice there's a little angle here, 23.5. You may have heard of that before, right? That's the same angle. So if we think about this is the sun, okay? This is the Earth. The Earth is going around the sun. That it's not rolling. Okay. So now, if it were straight up and down, doing this in the same plane, right? Then this degree tilt would be 0. But in fact, it's tilted. And so it rotates like that as it goes around. Everyone's familiar with this? That's the reason for seasons. You know this, right? Okay. Okay. So some of the terminology we need here, we have a north celestial pole. That's just our north pole projected onto that dome. This is the celestial equator. That's the equator, our equator on that circular dome. We have one in here. They must be.
I don't think we'll do.
Yeah, remember how we had that like big sphere for Astro 2300? All right, it's fine.
You can ride.
And that's the ecliptic. So this is the way. Oh, let's go back. Okay. Oh my gosh. Holy jeez and crackers. My God. Okay. So that's the picture I just showed you. That's our picture, right? How we view ourselves. And that's reality. Did you see that difference? Let's go back and forth. 1, 2, 1, 2. You good? Okay. All right. So how do we describe everything? You'll need this in order to point things in the sky. Okay. Directly overhead is called zenith. Yeah. Okay. What's the edge in all directions? Flat. Oh, very good. Yeah. Horizon. That's altitude 0. Let's go. And if I want to tell you where to look, okay, I just start north. Okay. And then I go either this way or that way. So if I go, let's say that's south, and that's west, and that's east, and there's north right there. Right? So let's say I want to find, go ahead.
Super random question. Have you ever watched something that's like determined like flat earther?
Yeah,
Yeah.
Astro 1000. That
Whoa.
was fun.
How'd that go?
I broke it. Oh, shit. That's not hard to do. It's very easy to do. Okay, so let's start with north, right? Let's start with north. We look at the north, and let's say I want to find where Giselle is. Okay, so for me personally, I need to look at roughly the horizon in the southeast. That may not be the case for you, right? So if I'm over here, okay, and I'm looking north, west. You see how there's words on each of the walls that are helping me?
Yes.
Okay, that's not the true north, right? The true north is in that direction.
Right.
Okay, that's not what we're saying. You're talking about this orientation in the room. If I want to show you where anything is in the sky, I'm going to use north, east, south, and west, and then I'm going to use a very simple angle. That'll be angle above the horizon. So I'm going to start down here, and I'm going to say, oh, it's like up there, 20 or 30 degrees. And remember, we just did all this fun stuff with our hands.
Oh.
This, that, this, right? I can go 1, 2, 3. Oh, that's about, 75 degrees up. That makes sense? Kind of useful. Right? Yes or no? Okay.
So say. if
Oh
you,
my
like,
God.
We're working with the telescope,
Mm-hmm.
that would already take into account. As
Sometimes.
far as like. Okay.
So when you decide to pick something in the sky, you'll need to look at its azimuthal, like how high up in the sky is. If it's near the horizon, it'll be hard to see for technical reasons. So you want it to be overhead. And so you're going to plan observations, which means you'll look inside of the planetarium software. You'll put your time and date of your observation in the future, and it'll tell you its location. And you have to be able to interpret the numbers that it tells you. You're like, oh, that will be in the sky or not, right? You have to be able to figure that out. Okay. Fair? Can you see all the stars all the time? No. Which stars don't you have access to? South Star is good, and? What do you mean equator?
Like, I guess. Radial from the equator.
Yeah, another way to say this is anything below the horizon, I can't see. Okay, that might seem like a dumb statement, but it's really not. So if you look and I tell you that the altitude of the star is -5 degrees, what does that mean? Below the horizon, not seeable. So you go into that planetarium software, you find your observation, like I'm going to do it this Thursday when the moon is gone so that I have really good conditions. I know that we have really good skies, and you type in, you're like Saturn, and it's like -35. Like, fuck, right? But if you see something like +83, is that good or bad? Good. What is directly overhead? 90. Ideal. Why is directly overhead ideal?
Means you'll always be able to see it.
It means you'll be able to see it. Good. It's directly overhead. Not Reed. Not Isabel. Not Giselle. Someone who doesn't work at the observatory.
In US.
Yeah. Why is seeing something directly overhead better than not seeing it directly?
I'll never not see it.
You don't move. Remember the
Like 30 minutes once.
Yeah, but if it's directly overhead, I'm telling you that's probably the best time to observe it. So let's imagine for a moment that we are thinking about how stars move in the sky.
This is the most stable.
Hold on, let's finish this one first thought and we'll come back to it. So stars rise in the east and they set in the west. Is that correct? The sun rises in the east and it sets in the west. So all of the stars in the sky are moving except for the North Star. Everything in the sky is moving except for the North Star. Right? The moon is even going from east to west every single night. Right? Okay. So I know that as this star, let's say this is a star, it's moving from east to west. I'm telling you that it's not as good to view it here as it is to view it here. So if I wait wait, and I view it when it's right here, I'm gonna get the best response. It's nighttime.
Yeah, the sun's getting started.
When it's west, it's not gonna be as, because it's gonna be a lot of light. So the-
Okay, yeah, so you might have light pollution low in the atmosphere, but also you have a lot of atmosphere low in the atmosphere. So as I look off in that direction, let's think about the fact that if you look at a mountain, what color is a mountain very far away?
What time is it?
What? Purple, okay, kind of right.
So nice.
Blue. Mountains are blue far away. Are they blue when you stand next to them? No, not really. No, they are blue because the light scatters red, okay, out of the frame of vision. So you have this blue column in front of you. And that same scattering is going on when you see a star. So if you see a star low on the horizon, it'll look red, and then it'll rise and it'll change colors. It'll become its real color overhead, and then it'll become red again as it goes low on the horizon. Same reason why you have sunsets. Okay? So you want to wait for stuff to be mostly overhead, which requires you to understand how to use the planetarium software and project it forward in time. I'm going to observe on Thursday. I want to observe Jupiter. Now you step forward hour by hour. You'll watch Jupiter will move through the night. Okay, it'll be overhead at 11:30. Write that down, right? So I'll try to observe it at exactly 11:30. As opposed to, oh, it just rose. Let's take an observation. That'll be a garbage observation. This will be a good one. That makes sense? Unless there's a cloud mode. Is that fair? Okay, here's the daily motions. This is in which hemisphere? Not Kobe. Not undress. Not Isabel. Someone who hasn't taken Astro. Which hemisphere is this in?
Hemisphere.
Yeah. Northern or southern?
That's like that way.
Is it possible to know?
Probably. I don't know. It's hard.
Why is it north?
Is that Utah?
What? Because this is Utah.
Yeah, okay.
But the other trick here is that this is the North Star.
Oh, interesting.
That's the North Star. How long was this photograph taken? Wrong. Wrong. Why is this guess? How do you know?
Nighttime, probably.
It's nighttime. Good. We know that it has to be less than a day, right?
Yeah.
But how do we know that it's less than 24 hours?
The colors are less, they're not
I
dark.
know.
Not quite. I do hear where you're going, right? So they took a picture of the rocks, and then they took a picture of the background, and they superimposed them. So it's a fake image, right?
Because it'd be a full circle.
Because there'd be a full circle. If it was 24 hours, this circle would connect. So what fraction of the circle is present?
Like 270.
A third or a fourth, so like 8 hours. Make sense? Yes or no?
If you waited a whole 24 hours, wouldn't that like completely ruin whatever you're recording? Okay. Yeah, so, okay.
Okay. So this is the apparent motion that we see from the rotation of the Earth. The stars are not doing any moving. Okay. The Earth rotates, stars stay fixed. We leave open a camera. It shows that the stars move. Stars don't really move. Okay. The Earth does move in two different ways. So there is actual motion, right? We talked about this picture here, where we're going around the sun, bada bing, bada boom, and we're changing our orientation of the pole either towards the sun or away from the sun. Towards the sun is in summer in the northern hemisphere, and away from the sun is winter in southern hemisphere. Okay. The stars that we're going to see, they're the same, but their position relative to the sun is going to change. Okay. Anyone have a problem with how the Earth rotates? Yeah.
You said the moon rises from the east or west.
That's a good question. Yeah, where does rise?
Where's it east? I thought you said west.
All motion on a daily scale goes from east to west. Right? Everything sets in the west. Right? West coast, best coast. Right? Is that true? Yeah. East coast, west coast. Okay. All right. Does that make sense? Okay. The moon still is moving in the sky though. And you'll notice that when you start to observe it, like let's say you're tracking it with one telescope, and you'll see all the background stars stay where they are, the moon will physically move. It's so close to us and it's moving so quickly, you'll notice it in a single night.
What are we gonna have like that, like partial? You don't see it?
I don't know. We could put it into the list here. I have a list of like cool things that are going to happen in the sky. If that's happening, we should absolutely take observations of it. So we know why stars rise and fall. We know that we can't see every star in all of the night, right? We saw these pictures. This one makes sense. How stars rise. As I look towards the south, they're going to appear to move on these little arcs. And as I look towards the north, if I look high enough, they'll make little circles. Does 3D geometry make sense to people? All right, here's the clicker question. Let me know when you're ready. A, B, C, D, E. Fist on your chest. Let's vote on 3, 2, 1. Okay, so I got a couple, not enough information to tell. A few norths, a few east, a few south and west. Oh, let's explain it.
Explain what we chose or the right answer. I'm thinking it's not enough information because, I mean, we know that that's the North Star in the center, but like you can be facing any direction but pointed towards the North Star. That's like what I thought.
Is that true?
Well, like, so like, maybe that's a weird way of describing it, but I'm thinking like, if the North Star is here, and then I'm like facing this way, like this is what I'm thinking when I think I'm facing a direction and I declared this. But I could also look at the North Star from this direction. I don't know if that's right or not, but that's what I'm thinking in my head.
I was looking at this. That's the north and then the one.
So you thought this was good
Yeah.
based on this
Yeah,
picture?
which way? Which way?
You thought this picture was taken in this room.
No.
I think I'm just wrong.
I thought it's north and the North Star.
Oh, so the north and the north star might be related.
Yeah.
So that's why you picked north. Do you want to explain? Anyone else want to explain? Yeah.
Unless you know where this location is at, like, we kind of talked about it earlier. That
Mhm.
we don't know what it is north or south.
Okay, but I told you one of the stars, right?
Well, then, you know, it's in the north.
Then you know it's in the north,
Mhm.
and you have to be looking north to see it. Why is that? Or you have to be, you have this explanation about, well, it could be overhead and I'm looking east to see it over there. Right, it's pretty low on the horizon. And it's moving. So we said that stars go from the east to the west. If I were facing south, what would the sky look like? Would it have circles on it?
Oh, I guess if you're facing south, it'd be.
No, if I'm standing in the northern hemisphere, right where we are now, and I'm looking south, do you see circles?
Oh, no, I think it'd be
No.
stripes,
You
right?
see lines. You see lines that go across like this. One, right? They all go across.
Now I see. what you're
Now, if you stand this way and you take a long exposure, okay, you would see what? Lines that go over you, straight lines. Now, if you look this way, straight line. So where do you get circles? Only in the.
Only in the.
Make sense?
Yeah, makes sense.
Yes or no?
Yes.
Because we're in the northern hemisphere, and I told you this is Utah. You have to use all these extra factoids that I gave you. Okay? Next one. You already know this one. 10 minutes? No, okay, all right, we'll do that one then. So here's the circumpolar motion. Okay, there's north, there's east, and there's west. Maybe I should have had you draw it. Which direction are they going, right?
Next year.
They're going. Okay. So here's our location in San Bernardino. Stars near the north celestial pole are circumpolar and never set. A different way to say this, okay? Is this close to the equator? Sorry, go ahead.
How do you supposed to know which way is like the later photo, which one's the earlier photo of the star? All the lines are the same brightness. But not actually never mind.
Yeah, stars aren't going to change their brightness very much. Yeah.
Well,
That's okay. That's okay. We're thinking through all these concepts, right?
I think he's asking how are we supposed to know which way it's rotating? Like does it rotate clockwise or counterclockwise?
Right. So if you're looking north, then by definition, look at this room, right? So let's stand. We're all looking at this in the same way. This is north. So stars are going to rise in the east. They're going to go overhead to the west. But notice that if I turned around, they would look like they would move from east west. Is that clockwise or counterclockwise? This is clockwise, right? Whereas this is counterclockwise. It depends on which way you're looking.
But it would still be the same directions.
Because it's only created by our rotation.
Got it.
Right? Okay, is this location closer to the equator or closer to the North Pole? To yourself first.
I'm thinking the equator, because we don't have like full circles. If we were closer to the North Pole, shouldn't we see like a pole or like more of like full rings?
Okay,
See the night sky.
people agree with that? Yeah, say it louder.
So the equator, if you're closer to the equator, you're not gonna have full rings of like motion. But if you're like closer towards the North Pole, you should see full rings because you're basically like closest to zenith as you can possibly be. No, this is closer to the equator.
You guys
Because don't-
disagree?
No.
Raise your hand for closer to the North Pole. No one likes that. Raise your hand for close to the equator. Raise your hand for you don't want to choose. That's okay. That's fine. Okay. Yeah, so this is closer to the equator. And in fact, we can kind of see that. Because if you can tell how high up the North Pole is, you can also tell where your latitude is. This is how you navigate using the sky. This only works in the northern hemisphere. When you get to the equator, guess what happens to the North Star? It goes below the horizon. Not so useful anymore, right? Okay. So generally speaking, if the North Pole is if the North Star is overhead, you are where? Santa Claus. You're Santa Claus. That's correct. Or yeah. Right?
Is there a frame of reference?
Does that make sense?
Is there a frame of reference that the southern hemisphere uses to navigate, or is it just like?
Well, if you actually are navigating, you use all the stars.
Oh, okay, so.
Yeah.
Okay.
But many constellations. Yeah, they would use like the Southern Cross, for example.
Oh, okay.
We just happen to have one that's very close to our pole. Right. So it's easier to teach kids.
Nice.
Okay, questions, comments, concerns? That's what he just asked. There is no southern pole star. There is no southern pole star, but there are southern constellations such as the Southern Cross. Okay, so the fact that we don't see the same stars is the greatest evidence for a non-flat Earth, right? It's the easiest one. Call your friend up. Hey, I was just in Brazil. What stars did you see? I couldn't find the North Star. It was gone. You know, a flat Earth, you'd be able to see all the stars at all the time.
The moon was backwards.
Yeah, I don't know about that one. Oh, you mean upside down? Oh, upside down. Yes. I thought you meant backwards, like this way. Yeah, so that's another one, right?
I don't
So
think that.
we see, let's say, you can't really see it here. Maybe, yeah, no. Yeah. So like, let's say this is the way that we see the moon, and maybe there's like a little lava piece at the bottom, right?
Lava?
Yeah, let's say there's like lava, right? Like,
That's unreal.
no, we know this, right?
Like craters?
Lunar mare, the dark stuff on the moon is ancient lava that has been dried. Okay, we all know this.
Now we do.
Okay, and the white stuff is ancient highlands. Okay, so like nice white rock. Okay, white rock, lava. So this is the view that we all see on a day to day. We go to
Madagascar.
let's see, we go to Madagascar for vacation and to find some lemurs. The moon will look like this.
Wow.
Whoa.
What happened?
It's
We're upside.
Why? Yeah, we're upset. You're on the other side looking up at it, right? It didn't do anything, but we went like that.
I don't like that.
That's weird.
That's a weird one. You're like that. Right?
Yeah.
It's weird. Yeah.
It's a good thing only like 20 or 30% of the world's population lives below the equator. Because
Yeah.
they're like all sorts of weird. They're hanging on upside down. Yeah. Something like that. Well, most people live in Asia. And almost all of Asia is above the equator.
That makes sense. So they're screwing up they're the liars.
Yeah. And all of Europe is above the equator.
Hmm.
Right? So the first time that you get to the equator is in the middle of Africa.
Freaking
So-
Australia, New Zealand.
What us? Like
Ecuador. Also named
Ecuador.
Ecuador.
Oh.
Oh shit! Right? Does that make sense? What is the most southern state?
No.
No.
I was
That's
thinking
good though. I do like that.
Florida?
No, you'd think so, but you're forgetting.
Oh shit.
It's Hawaii.
Oh wow, that's cool.
Okay. So we should shoot rockets off from Hawaii, but it's very hard to do because you have to transport all of that material that's made in the US. In the US, you can transport it by train and by truck. And if you want to bring it out to Hawaii, you have to bring it out to one of the most remote islands in the world. So it's not easy to get stuff out there. But it is the most southern location in the US of the contiguous states. Other territories, I think, might be lower. Okay. All right. How many states are there? What?
there's
13 minus.
No, there are only 46.
I don't like that.
There are 4 commonwealths.
Ooh, yeah.
You can look that up later.
No.
Yes.
No.
I'm sorry. I am here to tell you the truth. I can only tell you the truth. There are 46 states and 4 commonwealths. Okay. It's just like the Commonwealth of Virginia. They're just like ways of creating a state that are not a state. They don't call themselves a state. They call themselves a commonwealth. We call ourselves a state of California, but that's a self-referential. We call other places by whatever names we want to.
Is Rhode Island in the state?
I don't know. You have to look that up. I don't remember what the 4 are. I just know that Virginia is not.
Oh, it's weird.
Okay. So let's time out with all the side talk because we do have to, in fact, get through a tiny bit of more content. RA and declination. So this is something called right ascension. This is measured in hours. There are 360 degrees in a full rotation of the Earth, and there are 24 hours in that same time period. So just like mapping degrees, we are going to be able to tell where something in the sky is based on the time. So if I tell you something is 12 hours and 56 minutes and 13 seconds, that is a location in space, right? It's that direction. Does that make sense? Now I only have to add one more thing, and that is the declination. This is another way of saying how high above or below the horizon is it. Okay? So you'll see this, RA and dec in the planetarium software. Generally speaking, unless you're really comfortable with using this, I would use the direction and the azimuth. Right? How high up is it? The altitude and the azimuth. Right? Those are gonna be easy. Yeah.
Is this based on your?
So you can, these RA and decs are fixed. So the actual object will have the RA and dec that is appropriate to the sky. It won't matter where you are on the planet. And then if you have a good software, you can put in where your location of the observation will be, and it'll tell you how high above your horizon it will be. And you'll notice that by changing your location in that software, these numbers won't change. That's just where it is on the night sky. But the altitude will change depending on whether or not you're the horizon or at the North Pole. Does that make sense? Okay. So how do we convert from those? Well, you can do some math. What's the angular separation between two stars, A and B? This is RA6, declination plus 60, and RA7, declination plus 60. You say 15 degrees?
It is already going to 24.
Here, let's have a look. Let's draw it. Okay. This would be declination. Would be 0. Would be minus 90. This would be plus 90. Okay. This is right ascension. Starts at 0, 6, 12, 18, 24. Those are perfectly spaced.
Yep.
How would you begin to start this problem? Yeah, sure. So we can start with that. Right?
So like 660.
660.
Irish.
760. Okay, good. And I want that. Okay, so you take 15 degrees?
Yeah.
Anyone disagree with that? That's fairly reasonable, right? There's a little hidden calculation in there that you didn't tell me about.
Wait, where are you getting these numbers?
So he looked here and he said, well, the difference between this one A is 6 and B is 7. That's an hour out of 24 hours. So then he said, well, an hour out of 24 hours is the same to 360 degrees as 15 degrees. A little cross multiplying. Okay, you could if you wanted. You might have just done it. All right, brilliant. Okay, so you do that really quickly, and you find out 1 hour in right ascension is equal to about 15 degrees. Okay. So is this the distance?
From us. How are they?
No, on the sky. We're only talking about angular distance.
Oh.
What if I did this? Oh, man.
Then we have to find like their midpoint or whatever. Or no, not their midpoint, the hypotenuse. Yep.
Oh, you want a Pythagorean theorem now?
Yeah.
So you just built in the Pythagorean theorem, right? You just did it really quickly when you did that original one. You didn't even notice you were doing it. You just took the difference between the two locations. X1 minus X2 quantity squared plus Y1 minus Y2 quantity squared square root. But since that difference was 1 squared is 1, square root of 1 is 1, you're done. Right? So you didn't even notice that you did it. That's also only true for flat geometries. Do we have a flat sky?
No.
Oh shit, we have a curved sky. So this is going to get really complicated really fast. Okay.
Ooh,
So you're going to need the law of cosines, and you have some small angle approximations that you can make. But you're going to be basically using stuff like this. So you just save these types of formalisms if you need to, right? If I ever ask you for an angular separation on the sky, what's the distance between two objects? You'll use this. You will not use Pythagorean theorem because they are not right angles. Does that make sense? They're curved. This is curved. Sphere. Okay, that's getting to know the sky. We'll talk about CCDs. We'll talk about the ins and outs of telescopes at a later point. Okay, so each of you, any questions on that before we move on to annotations? Okay, I know I just left it up there for a second, but that's because this is what I believe about equations. You have to use them to know them. We're not going to use them as a group. We'll use them when we actually have a planetarium software in front of us. Has anyone downloaded the planetarium software? Okay, it's in the syllabus, right?
probably.
And it's free, so it's fun to use. It's called Stellarium. It's very straightforward, and you can put in your location, can change time, put in locations, whatever you want. Okay, so each of you annotated your papers, so you're going to form groups, but whoever you're sitting to right next to right now is not in your group. You have to get up and move to another person. Oh no, I hate it. What? 2 people per group. 2 people per group. I know.
That's only next time. Three. 1, 2, 3, go.
You boobs? Oh my god.
That is wild. Here, and I'm gonna take your annotation. Yeah, what about you?
So each of you annotate your paper.
Oh, you're not gonna annotate the one that you have in front of you. We're gonna do different angles.
Note similarities. and
No, you're not gonna annotate that one. You're gonna do different.
Make sure it's small written summary of the main findings.
Wait, Kobe, yeah, why don't you come in here? Actually, I'm gonna behind us, see back there. Otherwise, they're not gonna go real quick. I apologize.
What's that?
They just took a long time to.
Yeah, I guess we're
It's a 5 steps.
and we're trying to
Okay.
balance the similarities and also the differences. Yeah. I did not go into the volumes very much. I looked at the first sentences. Anywhere else. No, this is
This is a different picture. Okay, don't worry, you'll get both. But you're gonna start with different ones. Okay.
Yeah.
Okay, so you have groups. What I'd like you to do first, before you start reading this one, is compare in the annotations. Oh wait, you guys were both not here last time, right? Did you read the lectures?
I watched the.
Okay. Then you can discuss. So note similarities and differences in the original annotation style, right? Did you see that you both had questions on the same type of words, right? Where there's specific phrases that didn't make sense to both of you. Can you explain anything that the other person didn't get? Right, so spend like 5 minutes doing that, 10 minutes doing that, and then we'll talk about what we're gonna do with these new papers. Because each group will produce a small written summary of the main findings of the paper. One person from each group will present. Did you hear that?
Okay.
Why? Oh no. Because that's a skill that you're gonna learn.
Cause that's a skill.
Okay, so spend 5 to 10 minutes, work up a summary, one paragraph. The one that you've already done.
See,
Yeah, you've already done. One you've already read. Yeah. Just gonna give you a brand new paper, absorb it in 5 minutes, write a summary. No, that's insanity.
Okay, so you underlined this, water vapor reservoirs is very dynamic, crazy. I didn't prioritize it more than experiential atmosphere.
Yeah, but, there's a person in facility that. So you may think like, oh, why do I care?
Okay, you could underline this. If you want, it's fine. It's you got deeper in here, you said.
So it's just kind of like,
Yeah. However, the August data set covers a narrow pictorial strip. Compass. Okay.
So then that's why. Study.
Narrow circle. Okay, okay.
So it looks like they're gonna put, whatever this is.
Not like. Yeah. Yeah, okay. Sick. So what's your summary? I guess we can start talking about something.
They write it like in the back. I don't want to. I read it there for you. I don't know.
Yeah, no, I mean, I'll try to do a good job, but we're definitely talking about, I feel like it was the main cream of the crop is gonna be like the graphs, the figures, right? So what do they notice from the graphs? And then how are we interpreting these graphs? And why is that? Why should we care?
Yeah,
Right?
yeah. But like this first graph, very similar. Well, I mean, kind of, it just tells us that. So these red dots are where the satellite. It's a lot less southern hemisphere.
Yeah.
Around this polar line.
That has to do with like the pressure. Yeah, northern spring this summer. Yeah, okay.
Is that
Southern wind, yeah. So from or what is it, spring or no? What is it? Autumn to winter, there you go. Yeah. So sorry.
Every paper will get a summary. The summary that you're working on right now is just on the work that you've already done.
Okay.
The groups are working together, understanding how you just read. And you so you will not be analyzing right now. So they can let, you know, like.
Of the water, maybe.
Yes, it's like.
You're gonna stand up and just say. Next one. Less one. Here, right? 3 or 4 lines.
Let's figure this out.
Look at how many words are in a paragraph in the scientific paper. No, look. Measure this.
Measure them. Yeah. Headboard looks like it has percent.
That's the problem. Justify.
God, yeah. All right, well. Like that. We're just gonna talk about it. Oh, what graph talks about it? They're like, here's a whole paper. Just read this and then you'll know. Oh, here you go. I don't know. Talks about it.
Higher altitude, higher quantity.
I don't know what that is.
Yeah, that's the summary, right?
This graph.
So.
There's isn't a quiz, right? What you're doing right now, the exercise you're doing is you're learning to read a kind of. What I'm asking you is to summarize it, that's what you're doing. But you would develop this skill, of keep throwing papers at you, and you'll keep reading. And you'll read through, right? Remember, we're not taking this word down like it's gospel. We're gonna analyze it and say, do we believe this? Do we not? First thing you have to do is see if you understand anything. So you look for words that you don't get, you ask your friends to explain this concept, if you understand this concept, that's what you do now, right? Then you will create a summary that you'll present next Thursday or next Tuesday. Right?
We're creating a summary now for next week.
That you'll present, you're creating a summary now.
Mhm.
Present it next Tuesday.
Cool.
You'll also then learn what you're gonna do with this other paper.
Today.
You'll learn at the end of it.
So we're not.
We're not presenting today.
You're not presenting today, sorry, you're not presenting today. You're creating a summary today. You're writing a summary today. Then you'll work with your partner to make the summary better, such that one of you will present it
Next week.
next Tuesday.
Okay. Think this more time.
About 15 pages, it's 4 or 5 paragraphs, 4 or 5 lines, right? One paragraph.
Some people like you're gonna read it.
Is a measure of the.
You should have already read it. Are you writing it somewhere?
Matter between an observer of the eye.
That's why we're reading it right now. That's how I got scared. Oh, shit.
Well, that's why you're having.
Yeah. It's like a percent, how do you say it? Percent. Reciprocal. It's like cinnamon. Synonym. They are synonymously cinnamon precipitals. Yeah, anyway. Okay. Just a weight of energy density. Precipitable. Yeah. How much it is water. Okay, sip. Yeah, all right, cool, great. So should we summarize this first page, is that what we should? Yeah. Yeah. Well, if we think about it, right, it's like 1 sentence, 2 sentence, 3, maybe talking about both of these graphs. So 1, 2, 3, and 4 sentences right there. Per figure. Yeah, just the bullet point idea, right? So let's say this is our summary. Yeah, last name here, so that's. How do you say this person's last name? That
Montagliati,
is it?
it's Italian.
It's. Well, cool. And it was. So big takeaway. Depending, so what can we say? We can say depending. Solar season. Or saturation. Saturated. Yeah. Measure. That we're taking all this. Sick. Well, first page. We have like